Okay. We can see that this force is going to tend to accelerate the wheel in the counterclockwise direction. Okay, so I want a vector to represent a rotation in the counterclockwise direction. Okay, now, motion in the counterclockwise direction, you say, well, there are a lot of vectors. There's this one, this one, this one, this one, this one. We just go around the circle and do our tangent vectors. Well, that's not a single vector that corresponds to one angular motion. Okay? The vector that we use to represent, say, an angular velocity is going to have to be a single vector that unambiguously represents the direction of rotation. And that vector we find this way. We take our right hand and we make our fingers point and curl so that they tend to rotate in the direction of motion, and our thumb will represent the vector that specifies that direction of motion. Okay? The direction of motion will be, the direction of our angular motion is the direction of my thumb, out of the blackboard, not even in the plane of motion. It can't be in the plane of motion. You have too many vectors that correspond to motion in the plane. There's a single vector out of the plane that completely specifies this. If my direction of angular motion is here, that means that my fingers have to be like this. It means that I have something rotating in this plane. Okay, if it's here, it means I have something rotating in this plane, but in the clockwise direction. So there's a single vector. My thumb represents the single vector. If the vector's in this direction, then I've got to put my thumb in this direction, and I've got no choice about where my fingers go. They have to go clockwise, and they have to go in the plane perpendicular to that direction. Okay? If I say this direction, I better be careful to choose one that I can actually turn my hand in. If I say this is the direction, well, I've got to put the thumb of my right hand in that direction. My fingers tell me, okay, rotating what I see as counterclockwise in this plane. If it's in this direction, then I'm in this plane, going in this, rotating in this direction. So that vector completely specifies how I'm rotating. Okay? It doesn't tell me the size of the circle or anything, but it does tell me my plane and my direction of rotation. Okay, so that's one version of the right-hand rule. And I used another version. Right here I've got coils of wire, and I've got leads and so forth, so I can put a current through, let's say, this coil right here, okay? If I put a current through this coil, let's say the current goes in this direction, it's going to be easier in my hand. If the current's in this direction, then my thumb tells me the direction of the magnetic field that's created by that current. So, current in this direction, my thumb goes this way, I have a magnetic field in this direction, okay? And if I have current running the same way in this coil, okay, I again get a field moving in this direction, a magnetic field that's pointing in that direction, which means that if I put a metal object here and release it, if the magnetic field's strong enough, it'll go shooting out of here. Okay, the magnetic field will project it right out of here in that direction. Okay? So, just another example of the right-hand rule, same rule. And it's very pervasive when you get into using vectors, okay? Well, now, another version of the right-hand rule says you do the cross product of R with F net, okay? Now, the R vector's this way, so and the F net vector's this way, and here's how the rule goes. I put my fingers of my right hand in the direction of the R vector. It could be this way or this way, any way you need to do it. But then I orient my hand so that if I curl my fingers, they can move toward the direction of the force. And the only way I can do that, well, if I do it like this, well, the force is not in this direction. If I do it like this, well, the force is not in that direction. I have to have my hand in, well, my fingers have to be not only pointing parallel to R, but they have to be perpendicular to the plane of the board in order that when I curl my fingers, I can curl them down toward the direction of the net force, and that gives me, again, the direction of the torque. Okay, so the torque is in this direction, and that tends to change the angular velocity in this way, which is in this direction, okay? So if I multiply the torque by a time interval, well, I'm sorry, we'll see in the next one, okay? My torque turns out to be a product of my moment inertia and my angular acceleration. Okay, so anyhow, if I apply the torque in this direction for some time interval, it's going to tend to give me, change the rotation in this direction. Okay, so, okay, now we'll summarize the implications of all this, and that's what we're ultimately really going to use, but we want to see where all this comes from.